Hello, I am Dr. Zenya Worth. In this video, we will be discussing systems of linear equations. We will be discussing the substitution method, the elimination method, and the matrix method. A system of linear equations is defined as when two or more linear equations are working together and have a relationship. A linear equation with more than one variable can have an infinite number of solutions. For example, just this equation 2x plus 5y equals 9, there are many combinations of x and y that can cause this to be true. However, a system of linear equations that has more than one equation will have a single solution that satisfies all equations. So if I have two unknowns and two equations here, there's a single set of values for x and y that will solve both of these equations because we assume that these equations are related. In this case, the solution x is equal to 2 and y is equal to 1 will solve both of these equations, and it will be the only solution that will solve both of these equations. To achieve this single solution, you need to have as many equations as unknown variables. You can solve a system of linear equations algebraically using either substitution or elimination, or you can solve it using matrix methods. Let's talk about substitution first. For substitution, you put one equation in terms of a variable by isolating that variable on one side of the equation, then substitute whatever the expression is for that variable into the second equation and solve for the remaining variable. Use that solution to solve for the first variable that you don't know. It's easier to see this with an example. So we have two expressions here, 2x plus 5y is equal to 9, 4x minus 2y is equal to 6. To start, let's choose one of these two equations and isolate one variable. I'm going to choose 4x minus 2y is equal to 6. I'm going to rearrange so that y is by itself on one side. Subtract from 6, add 2, and then I'm going to divide everything by 2. So let's go ahead, we take this, we divide everything in this equation by 2, and we achieve y by itself, where y is equal to 2x minus 3. I plug this expression for y into the other equation. So now I have something that y is equal to 2x minus 3. In my other equation, 2x plus 5y is equal to 9. Now I'm going to plug this expression in for y. 2x plus 5y, 2x minus 3, is equal to 9. Now I've eliminated y from this equation and I only have variables in terms of x. So I'm going to solve for x. Distribute the 5, 10x minus 15, and solve 12x equals 24, and x is equal to 2 is the solution to that. I plug my solution for x into the first equation and solve for y. So now that I have that y is equal to 2x minus 3, I plug in my solution for x, where x is equal to 2, and I solve that y is equal to 1. For elimination, you need to reduce the system into a single equation with a single variable, kind of like substitution. However, in this case, you take both equations as a whole, and you manipulate the constants in front of the equations to either sum or subtract them in such a way that you remove one variable. We're going to start with the same system of equations here, two unknowns, two equations. And we're actually going to manipulate the other equation in this case, the first equation, so that we have the same constant in front of both x values. So we start with these two equations. What I want is the constant in front of both of these x values to be the same. Right now they're not, one's 2 and one's 4. But I can multiply my first equation by 2 on both sides to achieve a solution where there's a 4x as there's a 4 as the constant in front of the x value. I'm not actually changing the relationship of the equation here. I'm just scaling it by a factor of 2. It's really important that whenever I multiply the 2x by 2, I multiply everything else in the equation by 2 as well. So if I make a change to one side, I have to make the same change to the other to keep the relationship in the equation consistent. So I multiply everything by 2, and I find that my new expression is 4x plus 10y is equal to 18. Now I'm going to subtract these two equations just like I would subtract two numbers, 12 minus 9. Instead, I'm subtracting 4x plus 10y is 18 minus 4x minus 2y is equal to 6. So I subtract like terms here, and I solve for y. You'll see that when I subtract 4x minus 4, it cancels out and becomes 0, which is what we were trying to do. We were trying to eliminate the x. Now I have 10y minus negative 2. Because it's 10 minus negative 2, I'm actually going to add 2. That will be 12y. And I'm going to take 18, since I doubled it, it's now 18, minus 6 is equal to 12. So I end up with the expression 12y is equal to 12, divide by 12, and my solution is y is equal to 1. Then I go back and I use what I just found for y to solve for x. I start with that's my other equation, 4x minus 2y is equal to 6. 4x minus 2 times y is equal to 6, so x is equal to 2. And now I have that solution for that system of linear equations. The last way that I can solve this is using matrix methods. We can much more easily express larger systems of equations with more unknowns and more equations. We can describe them more effectively using matrices and solve them more quickly, especially if we use some sort of graphical tool to help us. We need to set up a series of matrices that describe our system of equations. We're going to use the same example as before, but we want this example to look like this, where it looks like a series of matrices that are multiplied together. And if you were to multiply these matrices out, you would see that you arrive at the same system of equations here. But we call that notation AX equals B, where X is our unknown variable, A are the constants in front of those X and Y values, and B are the solutions or what appears on the right-hand side of those equations. So let's practice by describing our initial system of equations here in matrix notation. The constants that go in front of X and Y make up their own matrix. In this case, it's a 2 by 2 matrix. 2 times X plus 5 times Y is equal to 9. So 2 and 5 make up the first row of my matrix, and 9 is the term from the right-hand side. Same thing here, 4x minus 2y, those are the constants of my second equation, equal to 6. The reason that x and y are inverted here, it's not a row but a column, is because remember when I multiply matrices, I multiply the first row by the first column, and multiply the second row by the first column. So in this case, I am keeping it consistent where x is multiplied by 4, and negative 2 is multiplied by y, or 2 and 5. So now I have this set as a series of matrices. And in order to determine the solution for x and y, because these are currently my unknowns, you multiply the inverse of matrix A by B. So my solution for x, or my unknowns here, x and y, is equal to the inverse of matrix A times B. To find the inverse of this matrix here, I recommend using either some online tool or using a graphing calculator or MATLAB. Some sort of online calculator will help you find the inverse. So you can go ahead and find the inverse using whatever tool you are most comfortable with. You multiply that by B, matrix B, which is 9 and 6. So the inverse of 2, 5, 4, negative 2 is this, times 9 and 6. And even though this looks a little messy, you actually end up with a solution of 2, 1, where x and y, the matrix x and y, is equal to 2 and 1, which means that x is equal to 2, and y is equal to 1. And that is your solution. I encourage you to try this out using new examples of linear equations. So in this case, I have 2 equations here and 2 unknowns. So you can solve this system of linear equations using substitution, elimination, and matrix manipulation. And in this case, I have actually 3 equations and 3 unknowns. So this might be a little bit harder to solve by substitution or elimination. It's definitely possible, but it's a little more difficult. Matrix manipulation might be a little easier here, but I highly recommend you try to solve both of these practice sets of problems using all 3 methods. I hope you will find this video useful in your class.